in the last lecture we discussed about the pre-envelope and complex envelope. Let's solve few questions on basis on complex envelope. The question number 45 from workbook is based on complex envelope. That the question is, a modulated signal is given by s of t equal to e to the power minus at cos in bracket omega c plus delta omega t ut, where a, omega c and delta omega are positive constant and omega c is very greater than delta omega. The complex envelope of s of t is. So s of t is a modulated signal, and this modulated signal is nothing but a band pass signal, because when we have modulated, that means the signal has been shifted to some frequency. It means it is now a band pass signal. So this is a band pass signal, it is given in the question. This is modulated signal, and modulated signal, that means band pass signal. So this is a band pass signal. So if it is a band pass signal, so from the concept of complex envelope, we know that any band pass signal can be represented in terms of complex envelope. So let's try to represent this band pass signal in the form of complex envelope. And because this is a modulated signal, it means there should be some carrier frequency, and the carrier frequency here is omega c. So if I represent it in the form of exponential term or the complex envelope, then this band pass signal s of t can be written as real part of e to the power minus at. This is already exponential term, so e to the power minus at will remain as it is, and this cosine is having exponential term e to the power j omega c plus del omega t. So the real part of this exponential term is actually a cosine signal. So if I take the real part of this, we get the same signal. So this is the term, and this ut is a unit step signal, so this ut will remain same because it is not a complex number, so that will be included inside the real function. Now if I write real part of e to the power minus at and e to the power j delta omega t and ut and e to the power j omega ct separately, then by the definition of the complex envelope, we know that any band pass signal s of t can be represented in the form of complex envelope as real part of complex envelope of the signal multiplied with e to the power j omega ct. So the coefficient of e to the power j omega ct is nothing but the complex envelope. So this is the reference frequency or the carrier frequency. So the coefficient of this term is nothing but this term e to the power minus at, e to the power j omega j delta omega t and ut. It means this is nothing but the complex envelope. So this is defined as complex envelope, and this complex envelope is SCE of t, and which is equal to e to the power minus at e to the power j delta omega t and ut. So this is the one of the method by which we can solve the question, that is for complex envelope, and according to option, if you will see, this is the correct answer is option B. Now this is one method. So we have defined this complex envelope by other method also, and let's try to solve this question by that method. So this was first method, and let's try to solve the question by another method. And to solve this question by other method, we have to represent this band pass signal in some other form, that is in the form of in phase component and quadrature component. So we can write this s of t equal to e to the power minus at as it is, and this is the formula of cos a plus b, cos a plus b. So from there we can have two terms. If there is a formula of cos a plus b, then we can write cos a cos b minus sin a sin b. And ut. So from here we can see that this is a cosine term which is our carrier term, and this is the sine omega ct term, which is our quadrature term. So the coefficient of this in phase component is cos delta omega t, coefficient of this quadrature component is sine delta omega t, and there is already a minus sign. So if I want to write the in phase component of this band pass signal, it will be e to the power minus at cos delta omega t and ut, and the quadrature component is e to the power minus at sine delta omega t and ut. These two terms e to the power minus at and ut are common in both in phase component and quadrature component. So we can write this cos delta omega t as in phase component and sine delta omega t as quadrature component. Now the complex envelope is defined as xCe of t equal to in phase component plus j into quadrature component, coefficient of quadrature component. These are coefficient of quadrature component and in phase component. This is e to the power minus at and ut is common in both the term, so that is common. Coefficient of in phase component is cos delta omega t plus j into coefficient of quadrature component is sine delta omega t. Now this is cos theta plus j sin theta. Cos theta plus j sin theta is given by e to the power j theta, and theta is delta omega t here. So we can see that we are getting the same result as in the first method. So the correct answer is option B, and this is the second method by which we can solve the problem of complex envelope. Next is question number 46, the complex envelope of the band pass signal. The complex envelope of the band pass signal. So it is already given that this is a band pass signal. So x of t equal to minus root 2 sine pi t by 5 divide by pi t by 5 sine pi t minus pi by 4. Center about f equal to 1 by 2 hertz is. So again we have to calculate the complex envelope for this band pass signal. So we can solve this question also by two methods. So first of all, as you can see that there are two sine terms, and if there are two sine terms means we will have two frequency, but what is the center frequency? It is given to us. So the center frequency is 1 by 2 hertz. So if you calculate the frequency for this particular term, so here the omega is pi by 5, so frequency is omega by 2 pi, that is 1 by 10. So this term is having frequency f equal to 1 by 10 hertz, and this term is having frequency omega by 2 pi, and omega is pi here, so pi upon 2 pi, this is 1 by 2 hertz. So it means that this is our center frequency. So whatever will be the center frequency given in the question, that will be converted into a quadrature and in phase component. So this term will remain as it is, and we will convert this signal into quadrature component and in phase component. Okay, so whenever this type of question is asked, first of all decide which is our center frequency, and that center frequency is only convertible into a quadrature component and in phase component. So we will keep this term as it is. This x of t equal to minus root 2 sine pi t by 5 divide by pi t by 5, and this is sine a minus b. So what is the formula for sine a minus b? Sine a cos b sine pi t cos pi by 4. If there is a minus sign, then it is also minus sign, then cos b sine a. that is cos pi t and sin pi by 4. So sin A cos B minus cos A sin B. Now the value of cos pi by 4 and sin pi by 4 is 1 by root 2. So this is common in both the term, and this 1 by root 2 will be common, and this will be cancelled with this root 2, and there is a minus sign, so this minus sign is multiplied in this term. So what we will get? We will get x of t equal to sin pi t by 5 divided by pi t by 5, and this minus sign is multiplied, so we get cos pi t minus sin pi t. Now this is having the frequency 1 by 2, this is having the frequency 1 by 2, this is in phase component, this is quadrature component, so the coefficient of in phase component is 1 here, that means this term, because that is already common, so the coefficient is 1 and that is coefficient is also 1. So now we can write the in phase component of this x, the in phase component of x is sin pi t by 5 divided by pi t by 5, and quadrature component is also same, sin pi t by 5 divided by pi t by 5. Now we have to write complex envelope. So xCe of t is xit plus j xqt, and in these two terms this sin pi t by 5 divided by pi t by 5 is common, so this is sin pi t by 5 divided by pi t by 5, and in bracket we will left with 1 plus j only, and this 1 plus j, that is in Cartesian form, we can write in polar form, and in polar form it is equal to sin pi t by 5 divided by pi t by 5, and when we take the magnitude polar form, so this is magnitude and phase, imaginary part divided by real part, both are having coefficient 1, that means tan inverse 1, which is 45, so e to the power j pi by 4. So root 2 is the magnitude and pi by 4 is the angle, and this Cartesian form can be written in this polar form, that is magnitude e to the power j into angle. So root 2 e to the power j pi by 4, and this is our final answer. This is the complex envelope. And according to option, this is option C. So correct answer for this particular question is option C. Now this is the one method. We can solve this question also by second method. So let's solve this question by second method. We have signal x of t minus root 2 sin pi t by 5 divided by pi t by 5 sin pi t minus pi by 4. Now we also know that this bandpass signal can be represented in terms of complex envelope, real part of complex envelope and center frequency. So if we want to write in terms of complex envelope, then and that too in real part, so what will be the real part of e to the power j theta? So e to the power j theta has real part cosine. You can write like this, e to the power j theta is cosine plus j sin theta. How can we make this sin theta as real part? Because here we have a sine signal. So how can we make this sine signal as a real part? So for this we have to multiply it by j, e to the power j theta equal to j cos theta minus j square, that is minus and minus sin theta. So now we can say that the real part of this j e to the power j theta is sin theta and imaginary part is now cos theta. So we have a sine signal, so we can write minus root 2 sin pi t by 5 divided by pi t by 5 real part of j into e to the power j pi t minus pi by 4. If we write the real part of this, then this is, if we write real part of this, then this is minus sin theta, but here we have sin theta, so we have to keep minus sign here. If I take minus common, then it is e to the power j theta, it is minus j cos theta and plus sin theta. So real part, this is real part and this is imaginary part. So real part is sin theta when it is minus j e to the power j theta. So real part is sin theta when e to the power, this is minus j e to the power j theta. And now we can consider this minus sign here, and minus minus become plus. This is root 2 sin pi t by 5 divided by pi t by 5, and real part of, we can write this as j. J is nothing but the having magnitude having 1 and angle is pi by 2, because imaginary part divided by real part and there is no real part here for this j. So the real part is 0, that means the angle is infinity and the value is infinity and the angle will be pi by 2. So this is e to the power j pi by 2, and we can write e to the power j pi t and e to the power minus j pi by 4. Now we can also write root 2 sin pi t by 5 divided by pi t by 5, real part of e to the power j pi by 2 and e to the power minus j pi by 4. If we solve these two, we will get e to the power minus j pi by 4, sorry, plus j pi by 4, because this is positive and this is negative. So this is 1 by 2, this is 1 by 4, we will get 1 by 4 with plus sign. So this is plus sign, and e to the power j pi t. This is having a center frequency 1 by 2, f equal to 1 by 2. So the coefficient of this center frequency is complex envelope. This term is common and this will become the complex envelope, part of complex envelope. So now if I write complex envelope XCET, then we have root 2 sin pi t by 5 divided by pi t by 5, and the coefficient of this e to the power j pi by 2, the coefficient of e to the power j pi by 2 is e to the power j pi by 4. So e to the power j pi by 4. So this is our answer, which was option C. So in this way we have to solve the questions from the complex envelope, and the next question, question number 47, is also from the complex envelope. Let's try it. So next is question number 47. Consider the bandpass signal x of t equal to root 2 sinc t sin 101 pi t plus pi by 4. The complex envelope with respect to reference frequency fc equal to 50 Hz is. So the previous two questions we solved, that was also based on the complex envelope, and in the two previous questions I solved by both the methods. So I am going to solve this question by only one method, and one method is homework to you, and you can solve that question by your own, and if you find any doubt you can ask me. Okay, so x of t is given as root 2 sinc t sin 101 pi t plus pi by 4. Now here we have center frequency 50 Hz. So if I calculate the frequency from these two terms, so we will get the frequency as 1 by 2 Hz from here, and we will get another frequency 50.5 Hz from here, and our center frequency is 50. It means that the 50 Hz we can achieve from this term only. So this term will remain same. So root 2 sinc t, we will not change this term, and this term can be converted into the complex form in the terms of complex envelope, or this can be converted into the quadrature and in phase form. So any of the method you can apply. I am solving this question by this method, that any bandpass signal can be represented by, in terms of complex envelope, real part of xc of t e to the power j omega naught t. So the coefficient of this function, this center frequency, we will get complex envelope. So root 2 sinc t will be same. So this is x of t root 2 sinc t. This will remain same, and same as the previous question, this can be written in the form of real part of minus j e to the power j 101 pi t plus pi by 4. Same as previous question, because we have seen that if we want to write sine as a real part, we have to multiply it by minus j. Then now we have 101 pi t, and from here we can have 50 hertz. So how we can convert in the form of 50 hertz? So x of t equal to root 2 sinc t, real part of this minus j can be written as e to the power minus j pi by 2, because this is cos pi by 2 minus j sin pi by 2, and sin pi by 2 is 1, so we get minus j. And here e to the power j 101 pi t and e to the power j pi by 4. So this can also be written as root 2 sinc t, real part of e to the power minus j pi by 2 and e to the power j. If I take this 2 pi common, then we can write 50 plus 0.5 t and e to the power j pi by 4. So if we solve this, we will get 101, because this is 50.5 multiplied by 2 is 101 pi t. So in this way we can write. Now we have root 2 sinc t, real part of e to the power j. If I multiply this and if you solve these two, you will get minus pi by 2 and here e to the power j pi by 4. So you will get e to the power minus j pi by 4, and if you solve this, you will get e to the power j 100 pi t, and this is e to the power j pi t. Now this can also be written as, if we rearrange, we can write it as e to the power minus j pi by 4 e to the power j pi t and e to the power j 100 pi t. So this is the reference frequency. Here we get the center frequency f0 as 50 hertz. So the coefficient of this reference frequency will give complex envelope, and this term is common. Now the complex envelope will be xce of t equal to root 2 sinc t, and this is e to the power j. If I take j common, then pi t minus pi by 4. This is the final answer. Root 2 sinc t e to the power j pi t minus pi by 4. As you can see from the option, there is option C. So the correct answer for this question is option C.